Welcome. We're going to take a look at Day 2, Chapter 5, Section 3. And I'm not getting frustrated because I'm just getting better at this, but this is my fourth try as I'm having some technical challenges here. But I'm sure this one's going to go great. Okay, we are to use derivative of the function to find points at which f has a local maximum, local minimum, and a point of inflection. Which is kind of unusual because we would typically think of using second derivative for that. Let's see what happens here. I've already got a derivative. What we need to be aware of is that if f of x's derivative got me to here, so would f of x plus, whoops, not equals, but f of x plus 11 would get me there as well. Because the 11, or any constant, f of x plus pi equals, again, plus pi plus any constant would get me to that same derivative. So I don't know where this function exists, but I know some shapes along the way. And it's nice. It's a polynomial. It's pre-factored. I'm going to take advantage of that when I create my sign chart here. I know that interesting things happen at 1 and 2. That's where the slopes are 0. Slope is 0 at 1. In fact, I'm going to draw this as a double 0 at 1, and you'll see what happens. And this is not unique for polynomials. If we have a double 0, we get some interesting things happen. Okay, let's consider putting in the value 3. Put in 3, I get a positive squared is positive times another positive positive. Put in negative, or put in 0, gives me a negative squared positive. 0 would give me a positive here times a negative here, negative. And put in 1.5, I get 1/2 squared, that's a positive, times 1.5 would be times a negative, negative. And we're not used to seeing that go negative to negative, but that can happen, and it has a lot to do with this double 0. For those of you who have been around honors pre-calculus, that is husband, wife, brother-in-law in action on this derivative function. So what do I know about this? It's a smooth curve. It's a polynomial. It's coming down. It's leveling off at 1 something. I don't know what. 1 something. Like we said, I don't know how high it is, but I know it levels off at 1. And then it goes down again. It's a polynomial. It's smooth until we get to 2. 2 what? 2, I don't know. And then it continues to go up after that. And I say, well, that looks sort of like a 4th degree polynomial. Well, it ought to. The antiderivative of a 3rd degree, and this is clearly 3rd degree polynomial, would be a 4th degree polynomial. So let's see what we know. A, do we have any local maximums? Nope. We have absolute maximum. We don't even have an absolute maximum, so we have none. B, local minimum. Yep, at x equals 2. C, inflection point. Well, this one right here, cupping up, then goes down again, has to start cupping down, so we actually have one at x equals 1. Now, if you're noticing, looks like we also have another one cupping down, cupping down, cupping down. Somewhere in here, we go from cupping down and start cupping back up. But that would be the second derivative's job to find that one. So I'm going to go ahead and do that. But I suspect perhaps if they're just asking us to use first derivative, the only one we can find from first derivative is the slope, or excuse me, the inflection point at 1. So let's go ahead, second derivative. Y double prime, product rule. Plain old first function, x minus 1 squared, times derivative of second, 1, plus first function's derivative, 2 times x minus 1 to the first times the inside derivative 1 times plain old second. And I'm interested when the second derivative is equal to 0. I know it's always differentiable. Hang on there. And I'm going to go ahead and set this equal to 0, and I'm going to factor. I can factor an x minus 1 out of each of these two terms. And I'm left with just an x minus 1 here, and I'm left with, once that's factored out, a plus 2x minus 4, or I'm left with x minus 1 times x, 3x minus 5. So my zeros would be 1 and 5/3, and it's comforting that 5/3 is between 1 and 2 because that's where we expect our inflection point to be, somewhere between 1 and 2. Okay, not too bad. Again, x equals 5/3 part C. We could not get that with just the first derivative. Okay, now kind of an interesting problem. A lot going on here. They're telling us a lot about this curve f. They're telling me its position. They're telling me its slope. They're telling me how it's cupping, its concavity at all sorts of different points. Some of those, the derivatives don't exist. But here's what I know. X goes from 0 to 3. And we're asked to draw a sketch of this. So 1, 2, 3. The y values, the f ofs, go from 0 to 2 to 0 back to -2. So up to 2, down to -2. Let's put some points in place here. F of 0 is 0. F of 1 is 2. F of 2 is 0. F of 3 is -2. And our function exists only between those points inclusive. Okay, let's look at slopes. The slope at 0 is 3. That would be trying to rise at a rate of up 3 over 1. Its target would be like up here, but it's only doing that maybe for an instant. Its slope is like that. It's aiming above this target point. The slope at 1 is 0. All right, that kind of makes some sense. I must be or I could be curving down in there. Maybe I curve all over the place and get there, but could be curving down into that. The slope does not exist when I get to 2, and there's two ways that could happen. Maybe I have an infinite slope. Maybe it's coming out of here and coming straight down for a moment. Or perhaps there's some corner point. I'm just going to put it doesn't exist right now. That's going to help me remember. Slope doesn't exist there. The slope at 3 is -3. Well, -3 would want to, from this point back, go up 3, left 1. So it's kind of aiming instantaneously above there. So maybe it comes up here and curves down into there. Let's see. Second derivative. This is our cupping. At 0, it's going through there like a straight line. But at 1, it's cupping down. At 2 doesn't exist. Not very surprising that the second derivative doesn't exist when the first one doesn't exist. At 3, it's like a straight line, aiming right up here. Okay, let's see what we got here. When x is between 0 and 1, the f values, the positions are positive. Yep, they're all up. Between 1 and 2, yep, all the positions are above 0. Between 2 and 3, okay, all the positions are below 0. They're negative. The first derivative, or the slope, between 0 and 1 is positive. Well, all looks good so far. Between 1 and 2 is negative. Okay, got to get down there. Between 2 and 3 is negative. Yep, got to get down there. How about cupping? Cupping down 0 to 1. So yeah, I think I can do this. Cupping down from 1 to 2. Now, I talked about this maybe being infinity. I'm just going to have it cupping down and not looking like it approaches infinity. Let's see if this works. I'm not suggesting you couldn't do it and have it approach infinity. And from 2 to 3, cupping down, and that kind of makes sense because I know I'm aiming above, cupping down. And see how that creates that corner point? Whether this is approaching infinity or not, that would keep those from being differentiable at 2, but it is still continuous. So there we have it. Your curve would have to look something like that. Okay, been a while since we talked about particles moving. Now, particle could be moving left, right, along a line, up, down at 45-degree angles. So we're gonna speak about that, just moving in negative directions, moving in positive directions. First, we're going to find the velocity, and when it's a polynomial, it's a breeze. The velocity is just the first derivative of position, and first derivative of polynomial simple. 2t minus 4. That's part A. B, acceleration. Derivative of velocity, just 2. Our acceleration is constant. We are constantly accelerating. Okay. And now it says describe the motion from 0 on. So I'm going to say at t equals 0. We don't have seconds, days. We don't know what we're dealing with here. So at t equals 0, the particle is at position, let's put in 0. 3, let's put in 0. Velocity is -4. moving in a negative direction. Let's put in 0. And accelerating. Okay, that's terrible handwriting. And accelerating. Okay, so the next interesting thing we might want to talk about is when the velocity hits 0. That would be when t equals 2. So at t equals 2, the particle is at, put in 2, and I get, is that right? T equals 2? Yep. At t equals 2, and I get 4 minus 8, negative 4 plus 3 is at negative 1. And at t equals 2, velocity is 0, and comes to rest after t equals 2, the particle moves in a positive direction. After t equals 2, we're positive here, and continues to accelerate. Okay, so highly recommend for this one, you go ahead and give this guy a try. Pause the video. If you're in class right at this point right now, I'd say, hey, let's try this. Let's try to get some stuff written out here. Let's see how close our verbiage matches. So pause this. Okay, I noticed some of you didn't pause it. Pause it. Try it. All right, A. Our acceleration based on t is 3t squared minus 3b. Our velocity based on t is 6t. And we're going to start talking about what happens at t equals 0 because we want t is greater than or equal to 0. So at t equals 0, the particle is at, that was really lazy, is at, put in 0, is at 3, and at t equals 0 and moving in a negative direction. I've been putting 2 L's on acceleration, that's terrible. Negative direction with acceleration of 0. 0 what? Don't know our units, but it'd be 0 feet per second, something like that. Okay. The next maybe interesting thing to talk about would be if I set this equal to 0, I get t equals plus or minus 1 after a little bit of algebra, but I only want to use 1 because t is supposed to be bigger than or equal to 0. So at t equals 1, the particle comes to rest. Acceleration is 0. At, when t equals 1, I get 1 plus 3, 4, minus 1, minus 3 at 1, and is accelerating. After t equals 1, particle continues to accelerate and moves in a positive direction. That's what AP test would be looking for, something along those lines. We talk about when the particle comes to rest, where it's going, what its acceleration is. We try to hit each base at interesting times and maybe the intervals in between those. You could say from time equals 0 to time equals 1, the particle is. After time equals 1, the particle is. But we definitely want to hit when the this should be v velocity, this should be acceleration. When the velocity hits 1. or hits 0 at time equals 1 in this case. Okay, let's go. Boy, so far holding out pretty good. No lag time yet. Use the second derivative to find the local extrema. How weird, we're used to using the first derivative to find local extrema. Let's see if this makes any sense. Use the second derivative test. Well, maybe we should look at the second derivative test, but let's find the second derivative first. Y prime equals, this is a product rule, plain old first times derivative of second, my favorite derivative. Finding the derivative of e to the x. Plus derivative of first 1 times plain old second, e to the x. Y double prime equals, still a product rule here. So all of that, actually I should do it this way I guess, all of that should look like this. Plain old first times derivative of second, plus derivative of first 1 times plain old second, e to the x, plus this e to the x that was already there, or x e to the x plus 2e to the x. I'm going to go ahead and I'm going to go ahead and factor this, just kind of a habit, e to the x times x plus 2, and then maybe we'd set it equal to 0, y double prime, but really not a lot of sense in that right now, but that would happen when x equals -2. But that's where I find inflection points. I use derivatives to help me find critical points for potential extremes. Okay, well let's take a look just for a moment at the second derivative test. Hopefully this works and you're seeing this. The second derivative test, and hopefully this makes some sense to us, says that if our slope is temporarily 0 and our second derivative is negative, then we have a maximum. If the slope is temporarily 0 and the second derivative is positive, we have a minimum. Well, let's give that just a bit of thought here. If the slope is 0 and the inflection or the cupping concavity is down, second derivative, we have a maximum. If slope is 0 and the cupping is up, we have a minimum. So let's find where the slope is 0. So y prime equals 0 when I'm going to factor this, e to the x times x plus 1 equals 0. So that would be x equals -1. And now I want to find out what f double prime of -1 is. F double prime of -1 is put in -1 here, and I get 1e to the -1st, and I get e to the -1st, or 1 on e, but that is positive. So at -1, the slope is 0, and the cupping is up. Therefore, we have a local minimum at -1 of, if I put -1 in here, I get -1 e to the -1st, or -1 on e to the 1st. Okay, hope that made sense. Let's take a look at example 5. If f of x is differentiable, what's differentiable mean? Hopefully you're all together saying smooth and continuous. And f prime of c is 0. So somewhere at c what? Doesn't really matter. We level off for a moment, just an instant. At an interior point C of f's domain, so somewhere in there, we level off. Must f have a local maximum or minimum C? So must it look like this or this? No, it could come up and level off and continue up. So that could indicate a slope of 0 where it continues up. So that is false. That may be, C may be the location of a stationary point where the function increases or decreases. C that. Okay, nothing wrong with having diagrams aid your explanation. Okay, 6. Sketch a smooth curve, y equals f of x through the origin. Smooth, like a polynomial kind of thing, through the origin with properties. So it goes through the origin, and then it says, don't read this f prime is less than 0. Read this, the slope is less than 0 when we are to the left. If you say f prime is less than 0 for x is less than 0, boy, I think it's easy to understand. The slope is negative to the left. Well, if the slope is negative, we're coming down like this. Now, it doesn't necessarily mean we're leveling off. I read ahead, sorry. But the slope is negative. It could be coming down like this. But then it has to be, the slope has to be greater than 0, so we have to be going up to the right, and it's had to be smooth, so I couldn't really come down and take a corner. Couldn't do that. It's supposed to be a smooth curve. So something along that line. Okay, I made it through the video without any real lag. There's the end of the assignment. Some of these are going to be pretty quick mechanical, but some of these we're going to have to put some thought, and heaven forbid we're going to have to actually do a little bit of writing here as well. Good luck. I hope that's helpful, and as always, stay tuned.